Hello there. I'm so glad you found your way here tonight. Right now, as your body begins to settle, take a moment to consider the extraordinary journey that brought you to this very instant. You are the result of millions upon millions of years of change, adaptation and survival. Every breath you take, every heartbeat, every flicker of thought in your mind carries the mark of an ancient lineage that stretches back through countless generations. Tonight we journey through the remarkable story of human evolution. Not as a lecture, but as a gentle exploration for curious minds ready to drift towards sleep. We will wander through deep time, from the first primates climbing through ancient forests to the moment our ancestors stood upright and gazed at the stars. From stone tools shaped by patient hands to the first cave paintings that spoke of dreams and wonder, there is no test at the end. No rush. No urgency. Just the peaceful unfolding of the greatest story ever told. The story of how you came to be. So let your breathing slow. Let your thoughts grow quiet. And allow yourself to drift into the gentle wonder of our shared ancestry. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable journey of our species. Either way, this space is for you. There is something deeply calming about contemplating our origins. Every bone fossil discovered, every ancient footprint preserved in stone, every trace of our ancestors carries within it a story, millions of years in the making. You are part of that story. The same evolutionary forces that shaped our earliest ancestors are written into your very being. The wisdom of deep time flows through your cells, your instincts, your capacity for wonder. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let the weight of the day drift away. And let us begin with the first of many quiet truths about human evolution. Evolution is patient beyond measure. Species change over thousands and millions of years. Traits that help survival are passed down through generations. Bones become fossils, and fossils become windows into the past. And yet, within all that slowness, there are sudden bursts of change, moments when new abilities emerge, when minds expand, when worlds open up. Tonight, we will wander through this magnificent journey. We will meet the ancestors who walked before us. We will discover the changes that made us human. And we will uncover truths about our origins that may surprise even the most curious minds. But there is no hurry. Evolution has been working for billions of years. It can continue its quiet labor while you rest. Let us begin with where it all started. All living humans share a single common ancestor who lived in Africa. Genetic studies have confirmed that every person alive today can trace their maternal lineage back to a single woman who lived in Africa roughly 200,000 years ago. Scientists often refer to this individual as mitochondrial Eve, not because she was the only woman alive at the time, but because her mitochondrial DNA is the one line that survived unbroken through all subsequent generations. Similarly, all men share a common paternal ancestor known as Y-chromosomal Adam, who lived at a different time but also in Africa. This does not mean these two individuals were the only humans of their era. Rather, their genetic lines are the only ones that persisted through the vagaries of chance and survival. The evidence for African origins comes from comparing DNA across global populations and finding the greatest genetic diversity within Africa itself, a signature of deep roots. Every human population outside the continent represents a subset of that original diversity. This shared ancestry reminds us that despite surface differences, all people belong to one extended family, shaped by the same evolutionary forces. Human evolution spans approximately 7 million years. The story of human evolution stretches back around 7 million years, to the time when our lineage split from that of our closest living relatives, the chimpanzees and bonobos. This vast timescale encompasses dozens of species that walked, climbed, and thought their way through changing environments. Most of these species are now extinct, known only from fossilized bones and teeth scattered across Africa and beyond. 7 million years may sound almost incomprehensible, yet it represents only a tiny fraction of life's history on Earth, which extends back nearly 4 billion years. During this period, our ancestors went from small, tree-dwelling creatures to upright walkers, tool users, and eventually the species capable of language, art, and technology. Each generation passed on small variations, and those variations accumulated into the profound differences that separate us from other apes today. Understanding this timescale helps put human achievements into perspective. We are newcomers, shaped by forces far older and slower than recorded history can capture. The first primates appeared around 60 million years ago. Long before anything resembling a human walked the earth, tiny creatures with grasping hands and keen eyes were clambering through the trees of ancient forests. These early primates arose roughly 60 million years ago, shortly after the extinction of the non-avian dinosaurs cleared ecological space for mammals to diversify. They were small, mostly nocturnal, and relied on agility rather than size for survival. Over millions of years, these ancestors gave rise to the incredible variety of primates we know today, from lemurs and lorises to monkeys and apes. The primate body plan, with its flexible limbs, opposable digits, and forward-facing eyes, proved remarkably successful in forest environments. Those adaptations for climbing and leaping became the foundation upon which later hominins would build. Without these early tree dwellers, the hands that now write symphonies and build spacecraft would never have evolved. We owe our dexterity and depth perception to creatures no larger than a squirrel scurrying through Paleocene canopies. Early primates had forward-facing eyes for depth perception. One of the defining characteristics of primates is the position of their eyes at the front of the skull, rather than on the sides. This arrangement gives binocular vision, allowing the brain to combine two slightly different images into a single three-dimensional view of the world. For animals leaping from branch to branch high above the forest floor, accurate depth perception was a matter of life and death. A misjudged jump could mean a fatal fall. Forward-facing eyes also proved useful for spotting ripe fruit among dense foliage and detecting the subtle movements of insects and other prey. Over time, primate brains became increasingly specialized for processing this complex visual information. The neural circuitry developed for tree navigation laid the groundwork for the sophisticated visual cognition that allows humans to read, drive, and appreciate art. Every time you catch a ball or judge the distance to a doorway, you are relying on adaptations honed in your arboreal ancestors millions of years ago. Grasping hands evolved before walking upright. Long before any hominin took its first bipedal steps, primates had already developed hands capable of gripping branches with precision and power. This grasping ability, enabled by opposable thumbs and flexible fingers, was essential for life in the trees. It allowed our ancestors to navigate complex three-dimensional environments, pluck fruit from thin twigs, and hold infants securely during travel. When some populations later came down from the trees and began walking on two legs, their hands were suddenly free for new purposes. Tools, carrying food, and eventually gestures that supported language all became possible because evolution had already provided the anatomical foundation. The sequence matters. Grasping hands were not an adaptation for tool use. They were repurposed after their original function became less critical. This is a common theme in evolution, where structures that evolved for one purpose are co-opted for another. Your hand, with its precision grip and delicate touch, is an arboreal inheritance turned into the most versatile manipulator on Earth. The extinction of dinosaurs opened ecological niches for mammals. For over 150 million years, dinosaurs dominated the terrestrial ecosystems of Earth, occupying nearly every major ecological role, from giant herbivore to apex predator. Mammals during this era remained small, mostly nocturnal, and marginal in the larger scheme of life. Then, around 66 million years ago, a massive asteroid struck what is now the Yucatan Peninsula, triggering a cascade of environmental catastrophes that wiped out all non-avian dinosaurs. This mass extinction cleared the stage for mammals to diversify and fill the empty niches. Within a few million years, mammalian lineages had exploded into a bewildering variety of forms, including the earliest primates. Without that ancient cataclysm, there is no guarantee that primates or humans would ever have evolved. The extinction of the dinosaurs was not a blessing or a curse, but simply a turning point that opened new possibilities. Our existence is, in part, an echo of that asteroid impact, a reminder that chance events can shape the entire trajectory of life on Earth. Climate change in Africa drove early human evolution. Over millions of years, the African continent experienced dramatic shifts in climate that profoundly influenced the course of human evolution. As global temperatures fluctuated and ice ages came and went, African forests expanded and contracted, sometimes giving way to vast stretches of open grassland. These environmental changes created new challenges and opportunities for the apes living there. Those that could adapt to more open habitats, perhaps by walking upright to cover ground more efficiently, or by exploiting new food sources, gained a survival advantage. Fossil evidence suggests that key evolutionary transitions often coincided with periods of climate variability, when only the most flexible populations thrived. The push and pull of wetter and drier phases may have spurred experimentation and innovation among our ancestors. Climate was not the only factor in human evolution, but it provided the backdrop against which natural selection acted. The savannas, woodlands, and lakeshores of ancient Africa served as the stage upon which the human story unfolded. Forests became savannas and shaped our ancestors' bodies. As Africa's climate shifted over millions of years, dense tropical forests in many regions gave way to more open woodlands and grassy savannas. This transformation had profound effects on the bodies and behaviors of the hominins living through it. In the forest, being able to climb quickly and move through the canopy was paramount. On the savanna, different skills mattered, covering long distances on foot, spotting predators across open ground, and enduring the heat of the tropical sun. Hominins that adapted to these new conditions developed longer legs, changes in the pelvis and spine for efficient walking, and eventually the ability to run for extended periods. The shift from forest to savanna did not happen overnight, but played out across hundreds of thousands of years, providing ample time for natural selection to favor those best suited to the changing landscape. The human body you inhabit today still carries the imprint of those ancient grasslands in its proportions and endurance capabilities. Walking upright freed our hands for carrying and tool use. One of the most significant consequences of bipedalism was that it liberated the hands from the task of locomotion. While quadrupedal animals use all four limbs for walking or running, upright hominins could carry objects over long distances without interrupting their travel. This ability opened new behavioral possibilities that would prove transformative. Early hominins could transport food back to a home base, share resources with kin, and eventually craft and carry tools. The freeing of the hands set the stage for increasingly complex manipulation and technology. Over time, the feedback loop between hand dexterity, tool use, and brain development accelerated human evolution. Skilled hands required sophisticated neural control, which in turn spurred the expansion of regions of the brain dedicated to fine motor coordination. Walking upright was not merely a change in posture, it was the gateway to a way of life built on carrying, making, and sharing, the foundation upon which human culture would eventually rise. Bipedalism is one of the earliest defining human traits. When scientists look for the characteristics that distinguish the human lineage from other apes, walking upright on two legs stands out as one of the oldest. Fossil evidence suggests that hominins were habitual bipeds millions of years before their brains began the dramatic expansion that would eventually produce modern humans. This means bipedalism preceded many of the traits we commonly associate with humanity, such as large brains, language, and advanced tool use. Upright walking required extensive remodeling of the skeleton. The spine developed an S-shaped curve, the pelvis became bowl-shaped, and the legs lengthened relative to the arms. These changes left clear signatures in fossils, allowing scientists to identify bipedal species, even from fragmentary remains. The evolution of bipedalism remains a subject of active research, with debates about whether it arose for locomotion, thermoregulation, freeing the hands, or some combination of factors. Whatever the initial driver, walking upright was the starting point for a cascade of evolutionary changes that would make us human. The oldest known bipedal ancestor is Sahelanthropus tchadensis. Discovered in Chad in the early 2000s, Sahelanthropus tchadensis represents one of the earliest members of the human family tree. Though known primarily from a remarkably well-preserved skull, this species displays features suggesting it walked upright, including the position of the foramen magnum, the hole through which the spinal cord exits the skull. In bipeds, this opening is located beneath the skull to balance atop an upright spine, whereas in quadrupeds it is positioned further back. Sahelanthropus lived around 7 million years ago, placing it near the very beginning of the hominin lineage, close to the split from the ancestors of modern chimpanzees. Some researchers debate whether this creature was truly a habitual biped, or still spent considerable time in the trees. Either way, its fossils offer a tantalizing glimpse of what the earliest hominins may have looked like. Sahelanthropus reminds us that the search for human origins often leads to unexpected corners of the African continent, far from the famous sites of East Africa. Sahelanthropus lived approximately 7 million years ago. At 7 million years old, Sahelanthropus tchadensis occupies a remarkable position at the very base of our evolutionary tree. During this time, Africa was forested in many places, but climatic shifts were beginning to create mosaics of woodland and open ground. The creature's environment was likely a mixture of trees and more exposed habitats, perhaps explaining why it seems to show adaptations for both climbing and upright walking. Dating fossils this old relies on geological context, analyzing the age of surrounding sediments and volcanic layers using radiometric techniques. The 7-million-year estimate places Sahelanthropus close to the point where the hominin and chimpanzee lineages diverged, though the exact timing and nature of that split remain the subject of ongoing research. What is clear is that by this early stage our ancestors were already distinct from the apes that would become chimpanzees. Sahelanthropus stands as a sentinel at the threshold of humanness, a witness to the very beginning of our journey. Ardipithecus ramidus could both walk and climb trees. Ardipithecus ramidus, known from fossils dating to around 4.5 million years ago in Ethiopia, offers a fascinating window into a transitional stage of human evolution. Its skeleton reveals a creature that was neither fully committed to the trees nor entirely at home on the ground. The pelvis and lower limbs show adaptations for walking upright, yet the hands and feet retained grasping abilities suited for climbing. The big toe, for example, was opposable, much like a thumb, ideal for gripping branches but less efficient for bipedal walking on the ground. This combination suggests that early hominins did not abandon the trees in a single leap, but gradually shifted their behavior over many generations. Ardipithecus reminds us that evolution rarely produces sudden, clean transitions. Instead, species often occupy intermediate states, blending old and new adaptations as they navigate changing environments. The story of becoming human is not a straight line, but a winding path through mixed habitats and mixed abilities. The famous fossil Lucy belonged to Australopithecus afarensis. Discovered in Ethiopia in 1974, Lucy is perhaps the most famous hominin fossil ever found. Her partial skeleton, representing roughly 40% of an individual, provided unprecedented insight into what early bipedal hominins looked like. Lucy belonged to the species Australopithecus afarensis, which lived between roughly 3 and 4 million years ago across East Africa. Her bones revealed a small-bodied creature who walked upright on 2 legs, yet whose arms were relatively long and curved, suggesting she still spent time climbing. The discovery electrified the scientific community because it demonstrated that bipedalism evolved long before the large brains that would come later. Lucy died around 3 million years ago, and her remains lay buried until an American paleoanthropologist spotted a fragment of her arm bone on a hillside. Her name was inspired by a Beatles song playing at the excavation camp that night. Today, Lucy resides in Ethiopia, a national treasure and an icon of human origins. Lucy stood just over 1 meter tall. At roughly 110 centimeters in height, Lucy was diminutive by modern standards, comparable to a small child rather than a fully grown adult. Her small stature was typical for Australopithecus afarensis, though males of her species were somewhat larger, indicating sexual dimorphism similar to that seen in some modern apes. Despite her size, Lucy's skeleton shows she was fully grown at the time of her death, likely in her mid-20s. Her short legs and relatively long arms gave her a different body proportion than modern humans, reflecting her mixed lifestyle of walking on the ground and climbing in trees. Standing little more than 1 meter tall on the African savanna, Lucy would have faced significant predators and needed every advantage her upright posture could provide, including the ability to spot danger and carry food or tools. Her compact frame challenges any assumption that early humans were simply smaller versions of us. She was a different kind of being, superbly adapted to her world. Australopithecus had brains about the size of a chimpanzee's. Despite walking upright and living in complex social groups, Australopithecus species had brains that were roughly the same size as those of modern chimpanzees, around 300 to 500 cubic centimeters. This is only about 1/3 the volume of an average modern human brain. The relatively small brain size tells us that bipedalism evolved before the dramatic expansion of the brain that would characterize later hominins. Intelligence, in the sense of planning, language, and complex problem-solving, came after our ancestors had already been walking upright for millions of years. Australopithecines were clever, certainly capable of finding food and avoiding predators, but their cognitive abilities likely fell within the range of living great apes. Brain size alone does not determine intelligence, but the subsequent tripling of cranial capacity in the genus Homo was accompanied by significant behavioral changes. Understanding Australopithecus as essentially small-brained bipeds helps us appreciate just how much evolutionary work remained to produce modern humans. The Laetoli footprints are over 3 million years old. In the Laetoli region of Tanzania, ancient volcanic ash preserved one of the most remarkable traces of early human ancestors, a trail of footprints left by at least 2 individuals walking side by side. These prints date to approximately 3.6 million years ago, making them among the oldest direct evidence of bipedal locomotion in the hominin fossil record. The footprints show a modern-looking arch, a non-divergent big toe, and a heel-to-toe weight transfer strikingly similar to our own gait. They are commonly attributed to Australopithecus afarensis, the same species as Lucy. Walking across wet volcanic ash that later hardened into rock, these hominins inadvertently left a message across millions of years, a message that says, "We walked here, upright and together." The footprints capture a single moment in time, when small beings paused in their journey across an ancient landscape. They remind us that fossils are not the only windows into the past. Sometimes the imprints of movement speak just as eloquently. Those ancient footprints show a remarkably modern walking pattern. Despite being over 3 million years old, the Laetoli footprints display a gait pattern that would not look out of place on a modern beach. The depth and distribution of pressure marks indicate that whoever made them walked with a heel strike, followed by a push-off from the toes, just as we do today. The big toe was aligned with the other toes, rather than splayed outward for grasping, a clear adaptation for efficient bipedal walking. This suggests that by the time of Australopithecus afarensis, the fundamental mechanics of human walking were already in place, even though other aspects of human anatomy and cognition had yet to evolve. The prints also show no evidence of knuckle impressions, or signs of the occasional four-legged gait seen in apes. These early hominins were committed bipeds, spending most of their time on 2 feet. The Laetoli footprints are a powerful reminder that walking upright is an ancient heritage, refined long before the emergence of our own species. Multiple hominin species often lived at the same time. One of the most surprising discoveries in paleoanthropology is that for most of human evolution, several different hominin species coexisted on the planet. Rather than a single lineage marching steadily toward modern humans, the fossil record reveals a branching tree with many twigs. At various points in the past, Australopithecus, Paranthropus, early Homo, and others overlapped in time and space. Some even shared landscapes and resources, potentially competing or occasionally interacting. This pattern of diversity was the norm rather than the exception until relatively recently. Only with the extinction of the last non-sapiens hominins, including Neanderthals and Denisovans, did our species find itself alone. The notion of multiple coexisting human relatives challenges the idea of a predetermined evolutionary path. Evolution experiments constantly, producing many variations, most of which eventually fade away. We are the lone survivors of a once bushy family tree, the last twig still growing. The genus Homo first appeared around 2.5 million years ago. Roughly 2.5 million years ago, a new kind of hominin appeared in Africa, one that would eventually give rise to modern humans. This was the emergence of the genus Homo, distinguished by changes in brain size, tooth shape and behavior that set it apart from earlier Australopiths. The earliest members, such as Homo habilis, showed modest increases in brain volume and a clear association with stone tools. The environment of the time was undergoing significant change, with expanding grasslands and fluctuating climates that may have favored adaptable, resourceful creatures. The appearance of Homo marks a turning point in evolution, the beginning of a trajectory that would lead to fire, language, art, and everything else we consider distinctly human. Of course, the transition was gradual and debated by scientists, with some fossils difficult to classify as either late Australopiths or early Homo. Nevertheless, around 2.5 million years ago, something new had undeniably begun. Homo habilis was among the first toolmakers. Homo habilis, whose name means handyman, earned its title through a close association with some of the earliest stone tools in the archaeological record. Living in Africa around 2 to 1.5 million years ago, these hominins were crafting simple, flaked stones that could cut meat, scrape hides, and crack bones for marrow. Though the tools themselves appear crude by later standards, they represent a cognitive leap, the ability to envision a finished product inside a raw rock and then execute the steps to create it. Earlier hominins may have used unmodified sticks or stones opportunistically, but Homo habilis is among the first to leave clear evidence of deliberate manufacture. The brain of Homo habilis was larger than that of Australopiths, though still far smaller than our own. This modest increase in brain size coincided with a lifestyle that increasingly relied on tools for survival. Homo habilis stands at the threshold of a new era, one in which technology became central to the human way of life. The earliest stone tools are called Oldowan tools. Named after Olduvai Gorge in Tanzania, where they were first identified, Oldowan tools are simple cobbles with a few flakes struck off to create a sharp edge. They represent the oldest known stone tool technology, dating back roughly 2.5 million years. Making an Oldowan tool required selecting an appropriate rock, typically one that fractures predictably, and striking it with another stone at the correct angle to detach usable flakes. Both the sharp flakes and the remaining core could serve as cutting or scraping implements. Though rudimentary, this technology persisted for hundreds of thousands of years, a testament to its effectiveness. Oldowan tools have been found across Africa and eventually in parts of Asia and Europe as hominins spread. They mark the beginning of a technological tradition that would gradually become more sophisticated, leading eventually to the hand axes of later periods. The Oldowan industry is the foundation upon which all subsequent human technology was built. Tool use marked a major cognitive breakthrough. While many animals use objects as tools, the deliberate manufacture of stone tools signifies a qualitatively different kind of cognition. To knap a stone, an individual must hold a mental image of the desired outcome and understand the cause and effect relationship between striking actions and the resulting flakes. This requires planning, spatial reasoning, and fine motor control coordinated by an increasingly sophisticated brain. The appearance of stone tools in the archaeological record is thus not merely evidence of technology, but a window into the minds of our ancestors. With tools, hominins could access food sources previously out of reach, such as the calorie-rich marrow inside bones, or meat from carcasses that teeth alone could not open. This dietary upgrade may have fueled further brain growth, creating a feedback loop between cognition and technology. Tool use opened new ways of interacting with the environment, setting the stage for the cultural evolution that would define the human lineage. Making tools requires planning and imagining the future. Crafting a stone tool is not a purely reflexive act. It demands the ability to anticipate needs and outcomes. The toolmaker must envisage the finished implement before striking the first flake and adjust technique in real time to achieve the desired shape. This capacity to project into the future, to imagine scenarios not yet present, is a cornerstone of human cognition. It underlies not only technology but storytelling, goal setting, and complex language. Other animals live largely in the immediate present, responding to stimuli as they arise. Hominins who made tools were stepping outside that present, thinking about meals yet to be eaten, hunts yet to be undertaken, and problems yet to be solved. The mental leap required for tool manufacture may have been one of the earliest expressions of what we now call foresight or mental time travel. In a very real sense, the first toolmaker was also the first planner, laying the cognitive groundwork for all future human achievements. Early humans used tools to access meat and bone marrow. Stone tools allowed early hominins to exploit food resources that would otherwise have been inaccessible. Sharp flakes could slice through tough hides and cut meat from carcasses, while heavier cobbles could crack open bones to reach the rich marrow inside. Bone marrow is an exceptionally nutritious food, packed with fat and calories that supported the energy-hungry brains of early Homo. Cut marks on fossilized animal bones, made by stone tools, provide direct evidence of this behavior millions of years ago. Early humans may have scavenged carcasses left by large predators, arriving quickly to extract what remained before competitors could. Over time, some populations likely became more active hunters, using tools to butcher prey they had brought down themselves. Access to meat and marrow marked a dietary shift away from the primarily plant-based diet of earlier hominins, providing the nutritional foundation for further evolutionary change. A richer diet helped fuel the growing human brain. The human brain is an extraordinarily expensive organ, consuming roughly 20% of the body's energy, despite comprising only about 2% of body weight. To support such a demanding organ, early humans needed access to high-quality, energy-dense foods. Meat and bone marrow, made accessible through tool use and possibly cooking, provided exactly that. As diets improved, natural selection could favor individuals with larger brains, setting off a feedback loop of better foraging strategies, improved technology, and further cognitive expansion. Some researchers call this the expensive tissue hypothesis, noting that as brains grew, digestive tracts shrank, a trade-off made possible by consuming more easily digested foods. Without the nutritional boost from meat and marrow, it is unlikely the human brain would have reached its present size. The foods our ancestors ate, and the tools they used to obtain them, were integral to the evolution of human intelligence. Human brain size tripled over the course of evolution. Over the span of roughly 3 million years, the average hominin brain volume increased from around 400 cubic centimeters to approximately 1,400 cubic centimeters in modern humans. This threefold expansion is one of the most dramatic changes in mammalian evolution, transforming not only cranial anatomy but also behavior, social structure, and ecological impact. The growth was not steady. Periods of relative stasis alternated with episodes of more rapid increase, often coinciding with environmental shifts or technological innovations. As brains grew, skulls had to accommodate them, leading to changes in face shape, jaw structure, and the birth process itself. Larger brains demanded longer childhoods, more parental investment, and richer diets. The cognitive abilities enabled by these bigger brains, including language, planning, and abstract thought, set humans apart from all other animals. Our oversized brain is both our greatest evolutionary asset and a constant reminder of how much our lineage had to change to produce it. Homo erectus had a brain about 2/3 the size of ours. Homo erectus, a species that appeared roughly 2 million years ago, possessed a brain averaging around 900 to 1100 cubic centimeters, roughly 2/3 the volume of a typical modern human brain. This was a significant jump from earlier hominins and represented a crucial step toward the cognitive sophistication of later humans. Homo erectus was the first hominin to adopt a fully terrestrial lifestyle, with body proportions similar to our own, long legs, shorter arms, and an efficient striding gait. Their larger brains supported more complex behavior, including the manufacture of more refined stone tools, the control of fire, and possibly rudimentary forms of language. Homo erectus populations spread across Africa, Asia, and parts of Europe, demonstrating an adaptability that earlier species lacked. The combination of a bigger brain and a modern-looking body made Homo erectus a pivotal species in human evolution, bridging the gap between the small-brained Australopiths and the large-brained humans to come. Homo erectus was the first hominin to leave Africa. For millions of years, hominin evolution was an exclusively African affair. Then, around 2 million years ago, Homo erectus began a remarkable migration that would carry human relatives far beyond the continent of their origin. Fossils of Homo erectus have been found in the Caucasus, in Indonesia, in China, and across much of Asia. This expansion required the ability to traverse diverse habitats, from tropical forests to temperate woodlands to arid landscapes. Homo erectus was equipped for the journey, a body built for efficient long-distance walking, a brain capable of flexible problem-solving, and tools that could be adapted to new circumstances. What drove this movement is uncertain, perhaps population pressure, pursuit of game, or simple curiosity. Whatever the cause, Homo erectus established humanity's first foothold beyond Africa, a precedent that later waves of migration would follow. This pioneering species opened the door to a planet-wide human presence. Homo erectus spread across Asia and parts of Europe. Following their initial departure from Africa, populations of Homo erectus dispersed across a vast geographical range. In East Asia, fossils have been found at famous sites in China, including Zhoukoudian near Beijing, and on the island of Java in Indonesia. In the West, remains from Dmanisi in the Republic of Georgia demonstrate an early presence in the Caucasus region. Each population adapted to local conditions, resulting in some regional variation within the species. Despite these differences, Homo erectus maintained a broadly similar toolkit and body plan across its range. The spread of Homo erectus foreshadowed the later global dispersal of Homo sapiens, although the older species never reached more remote landmasses, like Australia or the Americas. For nearly 2 million years, Homo erectus was the dominant hominin across much of the Old World, a testament to its evolutionary success. The legacy of this species includes the cultural and biological foundations upon which all later human populations would build. Homo erectus survived for nearly 2 million years. Few species in the hominin record can match the longevity of Homo erectus, which persisted from roughly 2 million years ago until perhaps 100,000 years ago in some regions. This success speaks to the adaptability and resilience of a species that weathered ice ages, volcanic eruptions, and the rise and fall of entire ecosystems. Over such a vast stretch of time, Homo erectus populations experienced countless generations of change, developing regional variations while maintaining the core traits that defined the species. They were not static, their tools became more refined, their use of fire more habitual, and their social structures likely more complex. The extinction of Homo erectus coincided roughly with the spread of Homo sapiens into the same territories, leading some researchers to speculate about competition or displacement. Whatever the cause, Homo erectus remains a monument to evolutionary endurance, a species that dominated the Old World far longer than modern humans have yet existed. Control of fire was a transformative moment in human history. The mastery of fire stands among the most significant milestones in human evolution, a technology that reshaped diet, social life, and even physiology. Evidence for the controlled use of fire extends back at least 1 million years, with some contested sites suggesting even earlier dates. Fire provided warmth in cold climates, light in the darkness, and protection from predators. It also transformed raw ingredients into cooked meals that were easier to chew and digest. Around the campfire, individuals could gather in the evening, fostering social bonds and perhaps the earliest forms of storytelling. Fire extended the usable hours of the day, creating time for tool manufacture, communication, and reflection. No other animal has achieved anything comparable. The control of combustion is uniquely human. The flames that our ancestors kindled millions of years ago still burn in our stoves and furnaces, connecting us to a tradition older than any recorded history. Fire allowed early humans to cook food and unlock more calories. Raw food requires considerable energy to chew and digest, and many nutrients remain locked within tough cell walls and fibrous structures. Cooking with fire breaks down these barriers, softening plant foods and denaturing proteins in meat. This process increases the caloric yield from the same quantity of food while reducing the time and effort spent eating. For early humans, cooking was a nutritional game changer, providing the surplus energy needed to support growing brains. Some researchers argue that cooking is so intertwined with human biology that our stomachs and intestines have shrunk, compared with those of great apes, a trade-off made possible by pre-digesting food with heat. The reduction in chewing time, meanwhile, allowed jaws and teeth to diminish, contributing to changes in facial structure. The simple act of roasting meat over a fire set in motion anatomical shifts that can still be seen in the mirror today. Cooking may have allowed our brains to grow larger. The human brain is metabolically expensive, consuming a disproportionate share of the body's caloric intake. For brains to expand as dramatically as they did, early humans needed a reliable source of high-energy nutrition. Cooking, by increasing the digestibility and caloric value of food, may have provided exactly that. The hypothesis, sometimes called the cooking hypothesis, suggests that without fire and cooked meals, the evolutionary increase in brain size would not have been possible. Raw food diets simply could not supply enough energy to sustain our ancestors, expanding brains while also meeting the demands of daily survival. If true, this means that cooking is not merely a cultural invention, but a driving force in human evolution. The fires our ancestors lit to roast their meals literally shaped the organ that would one day contemplate the stars. Cooking made the human mind possible. Fire provided warmth, protection, and a place to gather. Beyond its role in cooking, fire served multiple vital functions in the lives of early humans. In cold climates, the ability to generate heat meant survival through harsh winters that would otherwise be fatal. At night, a burning fire warded off predators wary of flames and smoke, providing a ring of safety in which groups could sleep. Perhaps just as importantly, fire created a social focal point, a gathering place where individuals could share food, exchange information, and reinforce social bonds. The campfire may have been the original community center, a space that encouraged cooperation and communication. Some researchers speculate that the extended evening hours provided by firelight allowed for the development of complex language and storytelling. Fire was not only a tool for modifying the environment, but also a catalyst for the social and cultural evolution that defines our species. Early humans likely shared stories around ancient campfires. While we cannot know exactly when language became sophisticated enough for storytelling, the conditions for it were present very early. Firelight extended the active day into the evening hours, creating a time when little else could be done but talk. Gathered around the flames, early humans may have recounted the events of the day, described dangers and opportunities, and perhaps began to spin tales that transcended the immediate moment. Stories can encode valuable survival information, teaching listeners about distant places and past events they never witnessed. They also bind groups together, creating shared identities and moral frameworks. The oral traditions of modern hunter-gatherer societies offer a glimpse of what these ancient sessions may have resembled. If language and fire co-evolved in a mutually reinforcing dance, then the flickering light of a campfire was also the birthplace of narrative, the spark that ignited the human gift for storytelling. The human body adapted to long-distance running. Unlike our closest ape relatives, who are built for short bursts of climbing and walking, humans possess a suite of adaptations for endurance running. Long legs, springy tendons in the feet, and Achilles, a narrow waist that allows counter-rotation of the torso, and large gluteal muscles all contribute to a running style that can be sustained for miles. The nuchal ligament at the back of the head stabilizes the skull during the jarring motion of a run, a feature present in runners like dogs and horses, but absent in chimpanzees. These traits began appearing in the fossil record with Homo erectus, and are refined in modern humans. The ability to run long distances opened new hunting strategies and allowed our ancestors to cover vast territories in search of food and water. Running is not merely a modern form of exercise, it is written into our anatomy, an inheritance from ancestors who outpaced prey on the African plains. Sweating allows humans to run for hours without overheating. Most mammals cool themselves by panting, a process that requires stopping or slowing down when body temperature rises. Humans, by contrast, have millions of sweat glands distributed across nearly hairless skin, allowing evaporative cooling even during sustained exertion. This remarkable thermoregulation system enables humans to run for hours in conditions that would cause other animals to overheat. Combined with our upright posture, which reduces the body surface exposed to direct sunlight, sweating made midday activity possible when competitors and prey sought shade. Early humans may have exploited this advantage to pursue game until the animal collapsed from heat exhaustion, a technique called persistence hunting, still practiced by some modern hunter-gatherers. The ability to sweat profusely is not a trivial quirk. It was a crucial adaptation that opened ecological niches unavailable to other predators. Every drop of sweat on a long run connects you to ancestors who survived by outlasting their prey. Persistence hunting may have been an early hunting strategy. Persistence hunting involves chasing prey over long distances until the animal, unable to cool itself efficiently, collapses from heat exhaustion. Humans, with their exceptional endurance and thermoregulatory abilities, are uniquely suited to this method. Some modern hunter-gatherer groups still practice persistence hunting, pursuing animals like kudu or wildebeest for hours under the hot sun until the prey can no longer flee. For early humans without sophisticated weapons, this strategy may have been one of the few ways to reliably obtain large game. Persistence hunting requires not only physical stamina, but also tracking skills and the ability to anticipate an animal's movements. Success demanded cooperation and communication, reinforcing social bonds within the hunting group. Although other methods such as scavenging and ambush were also likely used, persistence hunting showcases the unique physiological gifts that evolution bestowed upon the human lineage. Homo heidelbergensis appeared around 800,000 years ago. Between the era of Homo erectus and the emergence of modern humans, an intermediate species walked the earth, Homo heidelbergensis. First identified from a jaw found near Heidelberg in Germany, this species lived approximately 800,000 to 200,000 years ago across Africa and Eurasia. Homo heidelbergensis had a brain approaching modern size, a robust build, and a sophisticated toolkit that included carefully shaped hand axes and wooden spears. Many researchers believe this species is the common ancestor of both Neanderthals, who evolved in Europe, and Homo sapiens, who arose in Africa. If so, Homo heidelbergensis occupies a pivotal position in human prehistory, the trunk from which two major branches diverged. Understanding this species helps illuminate the evolutionary pathways that led to modern humans and their closest extinct relatives. Heidelbergensis represents a crucial chapter in the human story. Homo heidelbergensis used sophisticated wooden spears. Archaeological evidence from sites in Germany and elsewhere reveals that Homo heidelbergensis crafted wooden spears for hunting large game. At Schöningen in Germany, several well-preserved spears were found alongside the remains of butchered horses, demonstrating a coordinated hunting strategy. These weapons, dating back roughly 400,000 years, were carefully fashioned with a weighted balance similar to modern javelins, suggesting considerable skill and forethought. Creating such spears required selecting suitable wood, shaping it with stone tools, and hardening the tip in fire. The existence of these weapons implies not only manual dexterity, but also planning, cooperation, and probably some form of communication among hunters. The Schöningen spears shatter any assumption that sophisticated hunting behavior began only with modern humans or Neanderthals. Homo heidelbergensis was already a formidable predator, capable of taking down large animals through teamwork and technology. This species is the likely ancestor of both Neanderthals and modern humans. Based on anatomical similarities and the timing of fossil appearances, many paleoanthropologists consider Homo heidelbergensis to be the last common ancestor of Neanderthals and Homo sapiens. According to this view, populations of Homo heidelbergensis that remained in Africa eventually evolved into modern humans, while those that migrated into Europe faced different selective pressures and became Neanderthals. This branching occurred sometime between 500,000 and 300,000 years ago. The hypothesis explains why Neanderthals and Homo sapiens share many features absent in earlier species, as well as their ability to interbreed when they later encountered each other. Some researchers prefer different taxonomic schemes, but the general pattern of an ancestral population splitting into geographically separated lineages is well supported. Homo heidelbergensis thus serves as a crucial link in the chain that connects us to our closest evolutionary cousins. Neanderthals evolved in Europe and Western Asia. While modern humans were developing in Africa, a parallel branch of the human family tree was evolving in a very different environment. Neanderthals emerged in Europe and Western Asia, adapting to cold, glaciated landscapes that would have been hostile to their African relatives. Over hundreds of thousands of years, they developed distinctive anatomical features. robust bodies, barrel chests, and prominent brow ridges. Their stocky build helped conserve heat in frigid climates, while their powerful muscles aided in close-range hunting of large game like mammoth and bison. Neanderthals were not evolutionary failures. They thrived for at least 300,000 years, successfully navigating multiple ice ages. Their story is one of successful adaptation to challenging environments, a parallel experiment in becoming human conducted under very different conditions than those faced by our African ancestors. Neanderthals were brilliantly adapted to cold climates. The bodies of Neanderthals reveal a suite of adaptations finely tuned for life in Ice Age Europe. Their wide torsos and relatively short limbs minimized surface area, reducing heat loss in cold conditions. Their large nasal cavities may have warmed and humidified cold, dry air before it reached the lungs. Strong, heavily muscled limbs allowed them to bring down large prey in close combat, a necessity when much of the landscape was frozen grassland. Archaeological evidence shows they crafted warm clothing from animal hides, using scrapers and awls to process skins. They survived through glacial periods that would have challenged any tropical species. The cold-adapted physiology of Neanderthals stands as a testament to the power of natural selection, shaping a human form capable of thriving where few others could. Neanderthals had brains as large as or larger than ours. Contrary to outdated stereotypes of brutish, dim-witted cavemen, Neanderthals possessed brains that matched or even exceeded the average size of modern human brains. Their cranial capacities ranged from around 1,300 to over 1,600 cubic centimeters. Brain size alone does not determine intelligence, but it suggests significant cognitive capacity. Neanderthals created sophisticated stone tools, controlled fire, built shelters, and likely used some form of language. Their lifestyle required complex problem-solving, planning, and cooperation. The image of Neanderthals as inferior to Homo sapiens is largely a product of 19th century prejudice rather than scientific evidence. Modern research portrays them as intelligent, resourceful people who adapted brilliantly to their environment. Our shared ability to interbreed further underscores how closely related and how cognitively similar the two species truly were. Neanderthals buried their dead and cared for the injured. Evidence from multiple sites indicates that Neanderthals intentionally buried their dead, suggesting at least some awareness of mortality and perhaps ritual behavior. Skeletal remains have been found in deliberate grave-like positions, sometimes accompanied by objects or covered with stones. In addition, fossils of Neanderthals who survived severe injuries and illnesses show that they received care from others. Bones healed despite wounds that would have left individuals unable to hunt or care for themselves. This level of compassion implies strong social bonds and a sense of responsibility for group members. Such behavior was once thought unique to modern humans, but is now recognized as part of the Neanderthal repertoire. Caring for the dead and the wounded speaks to a rich emotional and social life, not so different from our own. Neanderthals made jewelry and used pigments. Recent discoveries have revealed that Neanderthals engaged in symbolic behavior, long considered the exclusive domain of modern humans. At sites across Europe, archaeologists have found eagle talons and shells that were apparently worn as ornaments, showing signs of deliberate modification and wear patterns consistent with suspension. Neanderthals also used red ochre and other pigments, possibly for body decoration or other symbolic purposes. Cave markings in Spain, dated before the arrival of modern humans, may even be the work of Neanderthal artists. These findings challenge the narrative that only Homo sapiens possessed the cognitive capacity for symbolism and art. Neanderthals, it appears, had their own aesthetic and perhaps spiritual traditions, expressions of an inner life we are only beginning to appreciate. Neanderthals were not primitive, but a different kind of human. For over a century, Neanderthals were caricatured as stooped, dull-witted brutes, inferior to the supposedly more advanced Homo sapiens. Modern research has thoroughly dismantled this stereotype. Neanderthals were skilled hunters, toolmakers, and possibly artists. They cared for their sick and buried their dead. Their brains were as large as ours, and their DNA lives on in many living people. Rather than a failed experiment or evolutionary dead end, Neanderthals represent an alternative path of human evolution, one shaped by the unique challenges of glacial Europe. They were not our inferiors, they were our relatives, cousins who walked a parallel road for hundreds of thousands of years. Understanding Neanderthals enriches our understanding of what it means to be human, by showing us the many forms humanity can take. Homo sapiens first appeared around 300,000 years ago. Fossil evidence now places the origin of Homo sapiens at roughly 300,000 years ago, considerably earlier than was believed just a few decades ago. Remains from Jebel Irhoud in Morocco exhibit a combination of modern and archaic features, suggesting that our species emerged through a gradual process, rather than a sudden event. Additional fossils from Ethiopia and other parts of Africa fill in the picture of a species slowly coalescing across the continent. The emergence of Homo sapiens was not a single moment when modern humans suddenly appeared. It was a mosaic process in which different modern features evolved at different times and places. By 200,000 years ago, fully modern anatomy was in place, setting the stage for the behavioral revolutions that would follow. Knowing that we are 300,000 years old gives new depth to the question of what makes us human. The oldest Homo sapiens fossils were found in Morocco. In 2017, researchers announced that fossils from the site of Jebel Irhoud in Morocco were the oldest known remains of Homo sapiens, dated to approximately 300,000 years ago. This discovery pushed back the origin of our species by 100,000 years and shifted the geographical focus from East Africa to North Africa. The Jebel Irhoud individuals had faces that looked strikingly modern, with flat, short faces and small brow ridges, though the back of the skull retained more archaic features. The associated stone tools and evidence of fire use suggest these early humans were behaviorally sophisticated as well. The find underscores that human origins were neither simple nor confined to a single region. Instead, Homo sapiens emerged across a broad African canvas. Morocco's role in this story is a reminder that Africa's entire expanse contributed to the making of modern humanity. Early Homo sapiens had a mixture of modern and archaic features. The earliest members of our species were not identical to people alive today. Fossils from 300,000 years ago show faces that look strikingly modern, with vertical foreheads and small brow ridges, yet the shape of the braincase was often more elongated than the globular skulls we have now. This combination of features suggests that the traits we consider typically human did not appear all at once, but accumulated gradually over tens of thousands of years. Different populations across Africa may have evolved different features at different times, eventually mixing and spreading. This mosaic pattern of evolution challenges the idea of a single moment of origin and highlights the complexity of human development. Understanding early Homo sapiens as a work in progress helps explain the diversity still present in modern humans. Modern humans evolved gradually across the African continent. Rather than a single birthplace, the origin of Homo sapiens appears to have been a Pan-African process. Fossil and genetic evidence suggests that different populations in various regions of Africa contributed to the emergence of modern humans. These groups were separated by deserts, forests, and vast distances, yet they periodically mixed as climate fluctuations opened and closed migration corridors. Over time, traits from multiple populations blended into the overall gene pool, giving rise to the anatomically modern form we recognize today. This multi-regional African model respects both the unity and diversity of early human populations. It means that no single valley or cave can claim to be the exact birthplace of our species. Instead, the whole continent served as a crucible in which humanity was forged. Different African populations contributed to our shared ancestry. Genetic research reveals that living humans carry ancestry from multiple ancient African populations that diverged and later reconnected over hundreds of thousands of years. Some of these deep lineages are still detectable in the genomes of people living in certain parts of Africa today. The mixing and remixing of these groups meant that modern humanity did not descend from a single small founder population, but from a network of interconnected communities. This genetic diversity provided resilience, allowing our ancestors to adapt to varied environments and survive catastrophic events. The richness of human genetic variation is a legacy of this complex African history, a tapestry woven from many threads rather than a single strand. Early humans in Africa developed increasingly complex tools. Over time, the stone tools made by early Homo sapiens in Africa became more refined and specialized. The Middle Stone Age, spanning roughly 300,000 to 50,000 years ago, saw the introduction of prepared core techniques that allowed craftspeople to produce standardized blades and points from a single block of stone. Tools were hafted onto wooden handles, creating composite weapons like spears and knives. Regional variation in tool styles suggests that different groups developed their own traditions, passing knowledge from one generation to the next. Some sites show evidence of long-distance exchange, with raw materials transported over considerable distances. This increasing complexity reflects not only growing cognitive abilities, but also deeper cultural transmission, the hallmark of the human way of life. The Middle Stone Age saw the first signs of symbolic behavior. Between about 300,000 and 50,000 years ago, humans in Africa began leaving traces of behavior that goes beyond mere survival. Archaeologists have found ochre crayons used for coloring, shells with holes drilled for stringing as beads, and geometric patterns engraved onto bone and stone. These artifacts suggest that people were creating symbols, objects whose meaning was shared within a community but did not derive purely from practical function. Symbolic behavior implies complex cognition, the ability to assign meaning to things and communicate abstract ideas. Whether these symbols served religious, social, or decorative purposes remains debated, but their presence marks a new chapter in human evolution. The Middle Stone Age was not merely a technological period, it was the dawn of culture as we know it. Shell beads from South Africa are over 70,000 years old. At Blombos Cave in South Africa, archaeologists discovered tiny snail shells pierced for stringing, dating back approximately 75,000 years. These beads represent some of the oldest known jewelry in the archaeological record. Their creation required selecting appropriate shells, perforating them with stone or bone tools, and threading them onto cord. The effort invested suggests the beads held significant value, likely signaling identity, status, or group membership. Similar shell beads from sites across Africa and the Middle East show that ornament making was widespread among early Homo sapiens. Adorning the body with meaningful objects implies a self-awareness and social complexity that we consider quintessentially human. These tiny shells are windows into the minds of our ancestors. Ochre was used for body decoration and possibly ritual. Ochre, a naturally occurring iron-rich pigment, has been found at archaeological sites associated with early Homo sapiens, dating back over 100,000 years. Lumps of ochre often show signs of grinding or scraping, suggesting they were processed to produce powder for coloring. The red and yellow hues may have been applied to skin, hair, or clothing for decoration or symbolic purposes. Some researchers propose that ochre could have served medicinal or practical functions, such as treating hides or repelling insects. Regardless of its specific uses, the widespread presence of ochre at human sites signals an engagement with color and perhaps with abstract ideas. Ochre represents one of the earliest substances deliberately modified by humans for purposes that transcend basic survival. Abstract patterns carved on bones hint at early symbolic thought. At Blombos Cave and other sites, researchers have found pieces of bone and ochre engraved with geometric cross-hatched patterns. These marks, dating back over 70,000 years, are deliberate and repetitive, suggesting intentional patterning rather than accidental scratches. What these designs meant to their makers is a mystery, but their existence implies minds capable of creating and interpreting symbols. The ability to represent ideas graphically is foundational to later developments like writing and art. Some scholars believe these patterns may have conveyed information about identity, territory, or ownership, serving as an early form of communication beyond speech. Even if these patterns were mere doodles, they reveal a species experimenting with abstraction in ways no other animal has been shown to do. The hands that carved these lines possessed an imagination that reached beyond the immediate moment. Early engravings are thus not just curious artifacts, they are signposts on the road to full symbolic culture. Language likely evolved gradually over hundreds of thousands of years. No one knows exactly when language first emerged, but most researchers believe it developed incrementally over a long span of time. Early vocalizations may have been little more than elaborated calls and gestures, gradually acquiring the grammatical complexity that characterizes modern speech. By the time Homo sapiens appeared, the anatomical prerequisites for speech, including a descended larynx and fine neural control of the tongue and lips, were largely in place. Language conferred enormous advantages. It allowed precise coordination during hunting, efficient transmission of knowledge, and the creation of shared stories and identities. Words could name things that were absent, describe events in the past or future, and articulate abstract concepts that had no physical form. The evolution of language is intertwined with the evolution of culture. Each reinforced the other in a feedback loop that accelerated both. Our ability to articulate complex thoughts and pass them on is arguably the single most important factor that makes us human. The human vocal tract is uniquely shaped for complex speech. Compared with other apes, the human larynx is positioned lower in the throat, creating a longer vocal tract capable of producing a greater range of sounds. The tongue is more mobile, able to shape rapidly changing frequencies into the distinct vowels and consonants of spoken language. The fine motor control required for speech is supported by specialized brain regions and neural pathways not found in other primates. These anatomical and neurological adaptations did not appear overnight. They evolved gradually as selection favored individuals who could communicate more effectively. The precision required to produce and perceive language is extraordinary, involving coordination of breath, vocal cords, and dozens of muscles in the face and throat. Our vocal apparatus is a finely tuned instrument, the product of millions of years of evolution toward ever more sophisticated communication. Language allowed knowledge to be shared across generations. Before language, skills and information had to be transmitted through observation and imitation, a slow and error-prone process. With words, a teacher could explain nuances, warn of dangers, and describe experiences far beyond the immediate environment. Stories could preserve the lessons of ancestors, allowing each generation to build upon the accumulated wisdom of those who came before. A grandfather could tell of droughts he survived decades earlier, preparing grandchildren for hardships they had never witnessed. This cultural ratchet meant that innovations no longer died with their inventors, but became part of a growing heritage. Language accelerated cultural evolution to a pace biological evolution could never match. Technologies, beliefs, and social norms could spread across communities and persist through centuries. The development of language transformed humans from clever apes into beings capable of limitless cumulative learning. Every word spoken today rides upon a tradition stretching back tens of thousands of years. Around 70,000 years ago, humans began leaving Africa in large numbers. While there were earlier, smaller migrations, the major out-of-Africa event began roughly 70,000 years ago and ultimately led to the peopling of the entire globe. Genetic evidence suggests that the populations that left Africa carried only a fraction of the genetic diversity present on the continent, a signature known as a population bottleneck. The triggers for this migration remain debated. Perhaps climate shifts opened previously impassable routes, or perhaps population pressure in Africa pushed groups to seek new territories. Small groups crossed into the Middle East, then spread in multiple directions, eastward along the coasts of Asia, and eventually to Australia, northward into Europe, and much later into the Americas. These pioneers encountered unfamiliar climates, flora, and fauna, adapting rapidly through both cultural and biological means. The diaspora that began 70,000 years ago would eventually result in human communities on every continent except Antarctica. It was the beginning of humanity's global adventure. Small groups crossed into the Middle East and beyond. The pathways out of Africa likely followed routes that are still debated by scientists. One major corridor led through the Sinai Peninsula and into the Levant, the region encompassing modern Israel, Jordan, and Lebanon. From there, groups could continue northward into Anatolia and Europe, or eastward into Central and South Asia. Another proposed route crossed the southern end of the Red Sea into the Arabian Peninsula when sea levels were lower. Regardless of the exact path, these migrations occurred in fits and starts, with populations expanding during favorable climates and contracting during harsher ones. Each wave carried with it a subset of African genetic and cultural diversity, seeding new populations that would eventually become distinct regional groups. The Middle East, sitting at the crossroads of three continents, witnessed some of the earliest mixing and splitting of modern human populations. Humans reached Australia at least 45,000 years ago. At a time when much of Eurasia was connected by land due to lower sea levels, a water gap still separated Southeast Asia from Australia and New Guinea. Crossing this barrier required watercraft capable of navigating open ocean, a remarkable achievement for any population. Archaeological evidence shows that humans arrived in Australia at least 45,000 years ago, and some researchers argue for even earlier dates. These first Australians adapted to environments ranging from tropical rainforest to arid desert, developing sophisticated technologies and complex spiritual traditions. Their descendants, the Aboriginal Australians, carry one of the oldest continuous cultural traditions on Earth. The arrival in Australia stands as one of the most impressive episodes in the human colonization of the globe. Reaching Australia required crossing open ocean. No matter the exact route, any journey to Australia from mainland Asia required maritime travel across stretches of water beyond sight of land. Even at the lowest sea levels during ice ages, the journey involved multiple island-hopping legs, and at least one crossing of around 90 kilometers, with no land in view. This feat demanded boats or rafts, knowledge of currents and stars, and the courage to venture into the unknown. It is among the earliest evidence of sophisticated seafaring anywhere in the world. Planning such a voyage required language, cooperation, and a willingness to take calculated risks. The first Australians were not pushed to their new home by accident. They deliberately set sail toward an unseen horizon, embodying the spirit of exploration that defines our species. Early seafaring shows remarkable planning and imagination. Building a vessel capable of ocean travel is no trivial task. It requires selecting materials, binding them together, and testing the craft in progressively challenging waters. Planning a voyage demands understanding of weather, currents, and navigation cues, such as stars, clouds, and bird flight. The decision to set out into the open sea with no guarantee of finding land on the other side suggests a level of imagination and confidence that goes beyond mere survival instinct. Early seafarers may have followed migrating birds, drifting debris, or simply trusted in the possibility of new lands over the horizon. Whatever their motivation, their success opened continents to human settlement and demonstrated that no barrier was truly insurmountable. Seafaring is one of the most striking examples of human ingenuity overcoming natural obstacles. Humans encountered Neanderthals in Europe and Western Asia. When modern humans expanded out of Africa and into the Middle East and Europe, they entered territories that Neanderthals had occupied for hundreds of thousands of years. The two populations overlapped for millennia, particularly in regions like the Levant and Central Europe. The nature of their interactions is difficult to discern from the archaeological record, but genetic evidence confirms that they did not simply avoid each other. They shared landscapes, resources, and perhaps knowledge. Some researchers suggest that early modern humans may have learned from Neanderthals, adopting elements of their technology or survival strategies. The encounter between our species and our closest relatives was not a single dramatic event, but a prolonged period of coexistence that left genetic and cultural traces still detectable today. Homo sapiens and Neanderthals interbred. One of the most startling discoveries of modern genetics is that Neanderthals and Homo sapiens produced offspring together. When researchers sequenced the Neanderthal genome, they found that non-African humans carry between 1 and 4% Neanderthal DNA on average. This interbreeding likely occurred in the Middle East or Europe when the two populations first encountered each other. The offspring of these unions were evidently fertile and integrated into the human population, carrying Neanderthal genes forward. Some of those genes may have provided advantages, such as immune system components adapted to Eurasian pathogens. The boundary between species is blurrier than once thought. Neanderthals were close enough to us biologically that reproduction was possible, making them not distant cousins but intimate partners in our genetic history. Most people outside Africa carry Neanderthal DNA today. If you trace your ancestry to Europe, Asia, or the Americas, you almost certainly carry DNA inherited from Neanderthal ancestors. This genetic legacy is relatively small, typically between 1 and 2% of your genome, but it is nonetheless a tangible link to another human species. The specific Neanderthal segments vary from person to person. Collectively, modern humans carry a substantial portion of the Neanderthal genome in fragmented form. Some inherited segments have been associated with traits such as immune response, skin and hair characteristics, and susceptibility to certain diseases. The presence of Neanderthal DNA in billions of living people is a humbling reminder that our species did not evolve in isolation, but absorbed and preserved contributions from those we met along the way. Denisovans were another ancient human cousin. In the early 2000s, geneticists extracted DNA from a fingerbone found in Denisova Cave in Siberia and discovered it belonged to a previously unknown hominin population. These Denisovans, as they came to be called, diverged from the lineage leading to Neanderthals sometime before 400,000 years ago and developed in Asia, while Neanderthals dominated the West. Remarkably little fossil evidence of Denisovans exists, just a handful of bones and teeth, yet their genetic signature is clear. They were a distinct group who also interbred with Homo sapiens. Denisovans remain mysterious, but their discovery underscores how many branches of the human family tree may still await discovery. The genetic age has revealed complexity in our ancestry that bones alone could never have shown. Denisovan DNA is found in some modern Asian and Oceanian populations. While Neanderthal ancestry is spread across most non-African populations, Denisovan DNA is concentrated in specific groups. Melanesians, including the indigenous peoples of Papua New Guinea and nearby islands, carry up to 6% Denisovan ancestry, among the highest proportions known. Lower but detectable levels are found in populations across Asia and among indigenous Australians. Aboriginal Australians and other Oceanian peoples likely encountered Denisovans as their ancestors migrated through Southeast Asia toward the islands beyond. This distribution suggests that early modern humans encountered Denisovans in Southeast Asia or the surrounding regions as they migrated toward Oceania. The genes inherited from Denisovans may have provided adaptive advantages, such as improved immune function or high-altitude tolerance. Like Neanderthal DNA, Denisovan heritage is a reminder that modern humans are a mosaic, carrying fragments of extinct relatives who contributed to our survival. The mixing of ancient human groups enriched our gene pool. Interbreeding between Homo sapiens, Neanderthals, and Denisovans introduced genetic variation that natural selection could act upon. Some of the acquired genes proved beneficial in new environments, helping our ancestors resist unfamiliar diseases, tolerate different climates, or digest novel foods. This infusion of diversity may have been especially valuable, as small migrating groups faced challenges their African ancestors had never encountered. Bottleneck populations with limited genetic variation are more vulnerable to disease and environmental change. The admixture with archaic humans may have helped counter these risks. Rather than contaminating a pure lineage, interbreeding enhanced the genetic toolkit available to future generations. The modern human genome is thus not a single, isolated heritage but a blending of multiple human relatives who shared their adaptations with each other. Our mixed ancestry is one of the reasons humanity has proven so adaptable across such a wide range of environments. Some inherited genes helped humans adapt to new environments. Researchers have identified specific genes acquired from Neanderthals and Denisovans that appear to have been positively selected in modern human populations. Variants affecting the immune system, enabling faster responses to local pathogens, are among the most frequently cited examples. Other inherited segments influence skin and hair characteristics that may have helped regulate exposure to ultraviolet light. Perhaps most dramatically, a gene variant from Denisovans helps Tibetans cope with the low oxygen levels of high altitudes. These borrowed adaptations provided shortcuts that our ancestors might otherwise have taken many generations to evolve independently. The exchange of beneficial genes between human relatives is one of the most striking examples of adaptive introgression in evolutionary history. Neanderthals disappeared around 40,000 years ago. After hundreds of thousands of years of successful occupation of Europe and Western Asia, Neanderthals vanished from the fossil record roughly 40,000 years ago. The exact timing and causes of their disappearance remain subjects of intense debate. Some researchers point to competition with incoming Homo sapiens, who may have had technological or social advantages. Others highlight climate fluctuations that shrank Neanderthal populations and limited their resources. Disease introduced by modern humans is another proposed factor. Volcanic eruptions and other environmental catastrophes may have contributed as well. Most likely, a combination of pressures tipped the balance. The disappearance of Neanderthals coincided with a period of rapid change in Europe, as Homo sapiens established themselves across the continent. What is clear is that after coexisting for millennia, only one human species remained. The world would never again know such diversity among our close relatives. The reasons for Neanderthal extinction remain debated. Scientists have proposed numerous hypotheses to explain why Neanderthals went extinct while Homo sapiens survived. Some emphasize direct competition for food and shelter, arguing that modern humans were more efficient hunters or had superior social networks. Others focus on subtle differences in reproduction or child-rearing practices that may have given Homo sapiens a demographic edge over many generations. A slightly higher reproductive success rate, compounded over millennia, could have tipped the balance decisively. Climate change, which brought drastic shifts in vegetation and game availability, may have stressed Neanderthal populations already in decline. New diseases carried by migrating humans could have devastated immunologically naive groups. In reality, the extinction was probably multifactorial, with no single cause definitively responsible. The disappearance of Neanderthals remains one of the most poignant mysteries in human prehistory, a reminder of how fragile even successful species can be. Homo sapiens eventually became the only surviving human species. For most of our evolutionary history, multiple hominin species coexisted on Earth. Neanderthals, Denisovans, Homo erectus, Homo floresiensis, and others occupied different regions and niches. By roughly 30,000 years ago, Homo sapiens stood alone. The transition to a single-species world is historically unusual. For millions of years, diversity was the rule. What made our species the survivor is unclear. It may be our capacity for complex language and culture, our willingness to explore and adapt, or simply luck. Whatever the cause, the world we inhabit today is one in which there is only one kind of human. Understanding how we came to be alone helps us appreciate both the contingency of our existence and the responsibility that comes with being the sole stewards of our lineage. Cave art appeared in Europe around 40,000 years ago. Some of the most breathtaking evidence of early human symbolic behavior comes from the painted caves of Europe. Sites like Chauvet, Lascaux, and Altamira contain vivid images of animals, handprints, and abstract patterns dating back tens of thousands of years. Chauvet Cave in France, among the oldest, features paintings over 36,000 years old. These images were created deep underground, far from natural light, suggesting deliberate, ritual-like journeys into darkness. The artists used natural pigments and the contours of the rock to give their creations depth and movement. Cave art speaks of minds capable of planning, symbolism, and perhaps spiritual contemplation. It marks a flowering of human creativity that continues to inspire awe today. The oldest known cave paintings depict animals and human hands. The subjects of early cave art are dominated by the animals our ancestors shared their world with: horses, bison, aurochs, mammoths, and deer. These creatures were often rendered with remarkable accuracy and dynamism, capturing motion and personality. Alongside the animals are stencils and prints of human hands, made by blowing pigment around a palm pressed to the wall. The meaning of these hand images is unknown, but they create a direct, intimate connection between the ancient artist and any modern viewer. Geometric signs, dots, and lines also recur across many sites, hinting at shared symbolic traditions. The focus on animals and hands suggests themes of identity, perhaps marking presence or communicating spiritual beliefs. These images are among the oldest visual narratives in human history. Cave art suggests complex symbolic and spiritual thinking. The placement of cave paintings deep within dark, difficult-to-reach chambers strongly suggests that these sites held special significance. The effort required to reach them, the preparation of pigments, and the flickering torchlight all point to experiences that went beyond casual decoration. Many researchers believe the caves served as ritual spaces where communities engaged with the supernatural or reinforced social bonds. The consistency of motifs across distant sites suggests shared cultural traditions or even beliefs transmitted over hundreds of generations. Whether these images were meant to ensure hunting success, honor the spirits of animals, or mark important events, they reflect minds capable of abstract thought and symbolic expression. Cave art is a window into the inner lives of our ancestors. Art also appeared independently in Indonesia at a similar time. While European cave art is famous, equally ancient imagery has been discovered on the other side of the world. On the island of Sulawesi in Indonesia, paintings of wild pigs and hand stencils date back over 40,000 years, rivaling the oldest European examples. Even older art, possibly over 50,000 years, has been found nearby. This simultaneous emergence of cave art in widely separated regions suggests that the cognitive capacity for symbolic expression was present in early Homo sapiens before they left Africa. Alternatively, the drive to create art may have arisen independently in multiple populations as a natural expression of human creativity. Either way, the Indonesian discoveries demonstrate that art is not a European invention, but a global human achievement. Musical instruments made from bone date back over 40,000 years. Archaeologists have discovered flutes fashioned from bird bone and mammoth ivory at sites in Germany dating back over 40,000 years. These instruments, with carefully spaced finger holes, were capable of producing complex melodies. Music, then, is not a recent cultural innovation, but a deep-rooted human behavior. Creating such instruments required advanced planning, selecting the right bone, hollowing it out, and boring precise holes. Playing them required breath control, fine motor skill, and a sense of rhythm. The presence of music so early in the archaeological record suggests it served important social functions, perhaps reinforcing group cohesion, marking ceremonies, or simply providing pleasure. The bone flutes of Ice Age Europe are among the earliest known musical instruments anywhere, and speak to a creative impulse as old as art itself. Creativity and culture became increasingly central to human life. As the Upper Paleolithic unfolded, the pace of cultural innovation accelerated. New tool technologies, regional artistic styles, and elaborate burial practices appeared across Europe, Asia, and Australia. Humans were no longer just surviving. They were creating identities, telling stories, and building traditions. This cultural explosion cannot be explained by biology alone. It arose from the cumulative effect of language, social learning, and the transmission of ideas. Creativity became a survival strategy, allowing populations to adapt rapidly to changing circumstances. Culture took on a life of its own, evolving faster than genes ever could. The capacity to imagine alternatives, to envision things that do not yet exist, set humans apart from every other species on the planet. Whether carving figurines, weaving textiles, or composing songs, our ancestors expressed an inner life that was rich, varied, and endlessly inventive. The world that emerged from the Ice Ages would be shaped not by biology, but by the ideas, technologies, and stories that humans invented and passed on. Humans crossed from Asia into the Americas around 20,000 years ago. The last major continental landmass to be colonized by humans was the Americas. Genetic and archaeological evidence suggests that the first Americans crossed from Siberia during the last ice age, when lower sea levels exposed a land bridge called Beringia. The exact timing is debated, with estimates ranging from roughly 20,000 to 15,000 years ago. These pioneers may have followed coastlines, hunting marine mammals and fishing, before moving inland as glaciers retreated. Some researchers propose even earlier arrivals, but the evidence remains contested. What is clear is that by 12,000 years ago, humans had spread throughout North and South America, reaching Patagonia at the southern tip. The colonization of the Americas was swift and successful, demonstrating once again humanity's remarkable adaptability. A land bridge once connected Siberia and Alaska. During the peak of the last ice age, so much water was locked up in continental glaciers that sea levels dropped by over 100 meters. This drop exposed vast stretches of shallow seabed, including the region between Siberia and Alaska known as Beringia. Far from being a narrow strip, Beringia was a broad vegetated landmass, home to mammoths, bison, and other megafauna. Hunter-gatherers living in northern Asia could have walked into the Americas without realizing they were crossing a continental boundary. The journey may have taken generations, with groups settling on the land bridge itself before eventually moving further. When the ice melted and sea levels rose, the bridge was submerged beneath the Bering Strait. The land that once connected the continents now lies beneath cold ocean waters, but its memory is preserved in the genes and cultures of the people who crossed it. Today, only 85 kilometers of frigid sea separate the two continents, a narrow gap that once was dry land. Within a few thousand years, humans reached South America. Once humans entered North America, they spread rapidly southward. Some moved along the Pacific coast by boat, while others trekked overland through corridors that opened as glaciers retreated. By around 14,000 years ago, archaeological sites in Chile and Brazil show clear evidence of human presence. The speed of this expansion speaks to the adaptability and determination of early Americans, who navigated diverse environments from icy tundra to tropical rainforest. Within a remarkably short span, they had colonized an entire hemisphere. The descendants of these pioneers would go on to develop the great civilizations of the Inca, Maya, and Aztec, cities and empires built upon millennia of innovation. From Beringia to Patagonia, the human journey across the Americas is one of the most impressive chapters in our global story. Humans adapted to every environment on Earth. No other species occupies such a vast range of habitats as Homo sapiens. From Arctic tundra to scorching deserts, from high mountain plateau to humid rainforests, humans have found ways to survive and thrive. Much of this adaptability comes not from biological evolution, which works slowly, but from cultural innovation, clothing, shelter, fire, and the social organization needed to exploit different resources. Humans domesticated plants and animals suited to local conditions, developed technologies appropriate to each environment, and built societies that managed everything from water scarcity to extreme cold. In the frozen Arctic, the Inuit fashioned kayaks and harpoons to hunt seals beneath the ice. In the Sahara, nomads learned to navigate by stars and find water in the driest landscapes. This ecological flexibility is arguably our most distinctive trait, a combination of clever minds, nimble bodies, and the cumulative wisdom of countless generations. We are the ultimate generalists, at home in any corner of the planet. Cultural adaptation became faster than biological evolution. Biological evolution requires generations for beneficial mutations to spread through a population, a process measured in millennia or longer. Cultural change, by contrast, can occur within a single lifetime. A new tool, technique, or idea can be invented one day and adopted by an entire community the next. This acceleration allowed humans to colonize new environments far faster than any species that relied on genetic change alone. When climate shifted or resources vanished, humans could adjust their behavior, their technology, and their social structures in response. Knowledge could be tested, refined, and handed down, accumulating improvements across generations at a pace genetics could never match. The rise of cultural adaptation as humanity's primary mode of survival marked a turning point in the history of life on Earth, setting us apart from all other organisms. Culture became humanity's second genome, a flexible inheritance that could be updated in real time to meet any challenge the world might present. Around 12,000 years ago, some humans began farming. The transition from hunting and gathering to agriculture is one of the most consequential shifts in human history. Beginning around 12,000 years ago in the Fertile Crescent of the Middle East, people started deliberately planting seeds and tending crops rather than simply harvesting wild plants. Similar transitions occurred independently in China, Mesoamerica, the Andes, and elsewhere. Farming allowed populations to grow beyond what foraging could support, but it also demanded new kinds of social organization. Settled life replaced nomadic wandering. Villages and eventually cities arose. The agricultural revolution was not an overnight event, but a gradual transition that unfolded over many generations. Its consequences, from surplus food to social hierarchy, continue to shape the world today. Agriculture arose independently in several regions of the world. Farming was not invented once and spread everywhere. Rather, it emerged independently in at least half a dozen different regions. Wheat and barley were first domesticated in the Fertile Crescent, while rice cultivation began in China. Mesoamerican peoples domesticated maize, beans, and squash, and Andean communities developed potatoes and llamas. Sub-Saharan Africa saw the domestication of sorghum and millet, while New Guinean farmers cultivated taro and bananas. Each center of origin adapted to local conditions, selecting crops and animals suited to the environment. The plants chosen in each region reflected what was available and what local populations knew how to cultivate. Over time, these crops spread along trade routes and migration pathways, mingling with other traditions. The multiple origins of agriculture demonstrate that, given the right circumstances, humans will invent similar solutions to similar problems. The drive to secure reliable food sources is a universal human impulse, expressed differently according to local opportunities. Farming allowed populations to grow dramatically. Agriculture produces far more calories per hectare than hunting and gathering, enabling communities to feed larger numbers of people in a smaller area. This surplus supported population growth that would have been impossible under foraging conditions. Villages swelled into towns, and towns into cities, as agricultural productivity increased. With more mouths to feed, the pressure to intensify farming grew, spurring innovations in irrigation, plowing, and crop rotation. However, larger populations also brought new challenges. disease spread more easily in dense settlements, and social inequality emerged as some accumulated more resources than others. The benefits and burdens of farming are intertwined, but one consequence is undeniable. Without agriculture, human populations would never have reached their current billions. Permanent settlements replaced nomadic lifestyles. For millions of years, hominins lived as nomads, following food sources across the landscape. Agriculture changed that equation. When crops required months to mature, people had to stay put to tend and protect them. Permanent villages appeared, built from mud, stone, or timber, depending on local materials. Living in one place allowed the accumulation of possessions that would have been burdensome for wandering groups. Houses, storage facilities, and communal buildings became fixtures of the human landscape. Permanence also meant attachment to specific territories, leading to notions of land ownership that would fuel both cooperation and conflict. The shift from mobility to settlement reshaped every aspect of human life, from family structure to social hierarchy. No longer did groups disperse and reconvene with the seasons. Instead, communities grew roots, both literal and figurative, that would anchor human societies for millennia to come. Domestication changed both plants and animals. The process of domestication transformed wild species into forms better suited to human needs. Wild grasses with small seeds became plump wheat and barley. Fierce aurochs gave way to docile cattle. Plants that scattered their seeds wildly were replaced by varieties that held onto their grains until harvest. These changes occurred over many generations as humans selected and bred the individuals with desirable traits. Animals became tamer, smaller, and more varied in color and form. In turn, humans adapted to their new partners, developing enzymes to digest milk, acquiring diseases from close contact with livestock, and building societies around the rhythms of planting and herding. Domestication reshaped both the domesticators and the domesticated. Wheat, rice, and maize became staples for billions of people. Three grains rose to dominate human diets across the globe. Wheat, first cultivated in the Fertile Crescent, spread across Europe and the Middle East, becoming the basis for bread and pasta. Rice, domesticated in Asia, fed billions from India to Japan and eventually reached every continent. Maize, developed from wild grasses in Mesoamerica, became central to civilizations, from the Aztecs to modern industrial agriculture. Together, these three crops now provide more than half of all calories consumed by humans. They shaped landscapes, cuisines, and economies. The societies that grew them rose or fell with their harvests. A handful of plants, selected thousands of years ago, still sustain the majority of humanity today. Dogs were the first domesticated animals. Long before anyone planted a crop or penned a sheep, wolves began to associate with human camps. The boldest among them scavenged scraps, and over time a partnership formed. Humans gained keen-eared sentinels and hunting companions. Wolves gained access to food and warmth. Generation by generation, these proto-dogs became gentler, smaller, and more attuned to human signals. Genetic evidence suggests domestication occurred at least 15,000 years ago, possibly earlier. Dogs learned to read human gestures better than any other animal, responding to pointing and gaze cues that even chimpanzees struggle with. This ancient bond remains unbroken, making dogs not just the first, but perhaps the most devoted of all our domesticated companions. Dogs may have been our companions for over 15,000 years. Archaeological sites across Europe and Asia contain dog remains dated to at least 15,000 years ago. Some researchers argue for even earlier dates, placing the origins of dog domestication beyond 20,000 years. What is certain is that dogs have accompanied humans through every major transition, from Ice Age hunting camps to the first farming villages, from ancient cities to modern metropolises. They have served as hunters, herders, guards, and companions. Their presence in art and burials suggests they were valued beyond mere utility. The human-dog relationship is one of the longest and deepest interspecies partnerships in history. Every modern dog breed, from tiny chihuahuas to massive mastiffs, descends from those first wolves who chose to stay. Villages grew into towns, and eventually into cities. With agriculture came settled life, and with settled life came growth. Small farming villages multiplied and expanded over generations. Some, favored by location or resources, swelled into towns with hundreds or thousands of inhabitants. A few grew further still, becoming true cities. Uruk in Mesopotamia may have housed 40,000 people by 3000 BCE, an unprecedented concentration of humanity. Cities required new forms of organization: walls for defense, temples for religion, markets for trade, and administrators to manage it all. Urban life brought both advantages and challenges, from cultural innovation to epidemic disease. Yet the trajectory toward ever larger settlements proved unstoppable. Today, more than half of humanity lives in cities. Writing was invented around 5,000 years ago. Around 3000 BCE, scribes in ancient Mesopotamia began pressing wedge-shaped marks into soft clay tablets. This system, called cuneiform, is among the earliest known forms of writing. At roughly the same time, Egyptians developed hieroglyphics, and similar systems emerged independently in China and Mesoamerica over the following millennia. The earliest texts are mostly mundane records: inventories of grain, lists of workers, receipts for trade goods. Yet writing's potential was quickly realized. Laws were codified, myths recorded, and histories preserved. For the first time, human thought could be stored outside the brain, transmitted across space and time, without the distortion of oral tradition. The invention of writing marks the end of prehistory and the beginning of recorded history. It is arguably the most transformative technology ever devised. Writing allowed knowledge to be stored beyond individual memory. Before writing, every piece of knowledge existed only in living minds. When an elder died, their wisdom risked dying with them. Writing changed that fundamentally. A clay tablet or papyrus scroll could preserve information indefinitely, available to anyone who could read it. Libraries became treasure houses of accumulated wisdom, storing medical recipes, astronomical observations, legal codes, and epic poetry. The Great Library of Alexandria held hundreds of thousands of scrolls, a monument to the power of the written word. Students could learn from teachers long dead, building on their insights. This cumulative effect accelerated progress in every domain. Knowledge no longer had to be rediscovered anew with each generation. It could be inherited, questioned, and improved upon. Writing transformed information into a permanent resource, the foundation upon which all later scholarship rests. Civilizations arose in Mesopotamia, Egypt, the Indus Valley, and China. Within a few thousand years of the agricultural revolution, complex civilizations emerged in several river valleys around the world. Mesopotamia's city-states flourished between the Tigris and Euphrates, while Egypt unified along the Nile under powerful pharaohs. The Indus Valley civilization built carefully planned cities like Harappa and Mohenjo-Daro, featuring advanced drainage systems and standardized weights. In China, dynasties rose along the Yellow and Yangtze rivers. Each civilization developed writing, monumental architecture, organized religion, and centralized government. Trade linked these regions, spreading ideas and technologies across vast distances. Though separated by thousands of kilometers and developing independently, these early civilizations faced similar challenges and devised comparable solutions. Their achievements laid the groundwork for all history that would follow. Trade networks connected distant communities. Even before civilizations arose, humans traded valued items over remarkable distances. Shells from the coast have been found hundreds of kilometers inland. Volcanic glass from specific sources spread across entire regions. As societies grew more complex, trade networks expanded exponentially. Mesopotamian merchants exchanged textiles for Indus Valley carnelian. Egyptian pharaohs imported cedar from Lebanon and gold from Nubia. Eventually, vast routes like the Silk Road connected China to the Mediterranean, carrying silk, spices, and ideas. Trade spread not only goods but technologies, religions, and diseases across continents. It created interdependence between distant peoples, fostering both cooperation and conflict. Merchants became diplomats. Caravans carried the seeds of cultural exchange. The global economy of today is the culmination of an impulse as old as civilization itself. Our interconnected world is not an invention of modernity, but a continuation of patterns established millennia ago. Human societies became increasingly complex and specialized. As populations grew, societies developed ever more elaborate structures. Early farming villages might have been relatively egalitarian, but cities bred hierarchy. Kings, priests, warriors, merchants, artisans, and laborers occupied distinct roles within an interdependent system. Laws codified behavior, bureaucracies tracked taxes and labor. Religious institutions provided meaning and legitimacy. Armies defended borders and enforced order. Craft specialization meant that individuals no longer needed to master every skill themselves. Trade allowed communities to benefit from the expertise of others. This increasing complexity was not always smooth or inevitable. Some societies collapsed when pushed beyond sustainable limits. Yet the overall trend over 10,000 years has been toward larger, more specialized, and more interconnected societies. Modern nations with millions of citizens and global trade networks are the current peak of this long trajectory. The complexity of our world is both a burden and a miracle. Technology accelerated the pace of cultural change. Every new technology builds upon those that came before, creating an ever-accelerating cascade of innovation. The invention of writing enabled laws and literature. The printing press spread ideas faster than any scribe could copy. The internet connects billions in real time. Each breakthrough expands the toolkit available to the next generation of thinkers. Agriculture took thousands of years to spread across continents, but industrialization transformed the world in mere centuries, and digital technology has reshaped society within decades. This acceleration shows no sign of slowing. The gap between invention and adoption continues to shrink, as cultural evolution outpaces biological evolution by orders of magnitude. Ideas that once took generations to spread now circle the globe in hours. The pace of change can seem overwhelming, yet it is simply the continuation of a trend that began when our ancestors first shaped stone. Human culture has become the primary engine of change on our planet, reshaping landscapes, climates, and the very fabric of life. Humans developed mathematics, astronomy, and medicine. Civilization brought the leisure and specialization needed for systematic inquiry. Mesopotamian scribes recorded astronomical observations and devised early mathematics. Egyptian physicians described diseases and treatments on papyrus. Greek philosophers sought universal principles underlying nature. Indian mathematicians invented zero. Chinese inventors created paper and gunpowder. Each culture contributed to a growing body of knowledge that transcended borders and eras. Medicine extended life. Astronomy predicted seasons and eclipses. Mathematics underpinned engineering and trade. Navigation relied on the stars. Architecture demanded geometry. Commerce required accounting. These fields were not separate from religion or philosophy in early times, but emerged gradually as distinct disciplines. The accumulation of knowledge over millennia laid the groundwork for the scientific revolution and the technological wonders of the modern world. The questions our ancestors asked about the heavens and the body continue to drive research today. Recorded history covers only a tiny fraction of human existence. Writing appeared around 5,000 years ago, giving us the historical record. Yet Homo sapiens has existed for roughly 300,000 years, and the human lineage stretches back millions. Recorded history thus represents less than 2% of our species, time on Earth, and a far smaller fraction of our evolutionary journey. The vast majority of human experience occurred in prehistory, known only through fossils, stone tools, and genetic traces. We tend to view history as the main event, but it is merely the latest chapter. Before writing, there were countless generations of hunters, gatherers, and early farmers whose lives left little permanent trace. They laughed, loved, mourned, and wondered at the stars, yet their names are lost to time. Their struggles and triumphs shaped the world we inherited. Remembering that history is only the tip of a very deep iceberg helps put our modern concerns into the perspective of evolutionary time. Evolution continues to shape humanity even today. Natural selection has not stopped. It has merely changed form. In modern populations, traits that affect survival and reproduction still vary and can shift over generations. Resistance to certain diseases, ability to digest particular foods, and other subtle differences continue to evolve. Human populations living in different environments show evidence of recent selection. High-altitude adaptations in Tibetans, lactose tolerance in pastoral groups, and resistance to malaria in tropical regions. Cultural changes also alter selection pressures, from medicine keeping alive those who once would have died, to reproductive choices influenced by economics and education. Even the way we live, our diets, exercise habits, and social structures can influence which traits are passed on. Evolution is not a finished story but an ongoing process, quietly shaping humanity even now. The forces that molded our ancestors continue to act upon us, in ways both obvious and hidden. Lactose tolerance evolved in some populations after farming began. Most mammals lose the ability to digest lactose, the sugar in milk, after weaning. For millions of years, adult humans were no different. But among populations that domesticated cattle and relied on milk, a mutation arose that kept lactose digestion active into adulthood. This trait spread rapidly through European and some African and Middle Eastern populations over the past 10,000 years. The advantage was clear. Milk provided a reliable source of calories, protein, and hydration, especially in times of famine or drought. Today, lactose tolerance varies dramatically worldwide, from nearly universal in Scandinavia to largely absent in East Asia. This is a textbook example of recent human evolution driven by culture. the decision to herd animals for milk created a new selection pressure, and genes responded within recorded history. It is one of the clearest cases of gene-culture coevolution in humans. High-altitude adaptations appeared in Tibetan and Andean peoples. Living at high altitude presents severe challenges. Thin air holds less oxygen, and the body must work harder to supply tissues. Populations that have lived in the Himalayas and the Andes for thousands of years show genetic adaptations to cope. Tibetans carry variants of genes that regulate red blood cell production, preventing the blood from becoming dangerously thick. Andean peoples developed larger lung capacity and increased blood oxygen saturation. Ethiopian highlanders show yet another set of adaptations, demonstrating that the same problem can be solved in multiple ways. These adaptations evolved independently in each region within the past several thousand years, demonstrating that natural selection can act quickly when the pressure is strong. The speed of these changes, measured in millennia rather than millions of years, underscores how responsive our species can be when facing new environmental challenges. High-altitude living is a natural laboratory for studying recent human evolution in action. Our evolutionary journey is far from over. Human evolution did not end when we invented civilization. It merely took new forms. As environments change, as diseases emerge and retreat, as cultures shift reproductive patterns, natural selection continues. Future generations may differ from us in subtle ways we cannot predict. Technology could also play a role. Genetic engineering and medicine may one day alter the trajectory of human evolution in deliberate ways. Whether this prospect excites or alarms, it underscores a fundamental truth. We are not the finished product of evolution, but a work in progress. We stand at a unique moment in history, capable of influencing our own evolutionary path for the first time. The consequences of the choices we make now may ripple through the generations yet to come. The story of human evolution is still being written, one generation at a time, including yours. You carry within you the legacy of millions of years of change. Every cell in your body contains DNA inherited from ancestors stretching back through unbroken lines to the first cells on Earth. Your eyes descend from light-sensitive patches in ancient worms. Your lungs evolved from the swim bladders of fish. Your hands retain the grasping heritage of primates who swung through forests millions of years ago. Every beat of your heart echoes the rhythms of countless ancestors who lived, survived, and reproduced. The calcium in your bones was forged in ancient stars. The iron in your blood carries oxygen just as it did for the earliest vertebrates. You are not separate from this vast history. You are its current expression. The past lives on within you, in the shape of your bones, the chemistry of your blood, and the wiring of your brain. When you feel wonder at the night sky, you share that feeling with ancestors who gazed upward tens of thousands of years ago. The story of human evolution is ultimately the story of you. All the facts you have heard tonight about primates and hominins, tools and fire, migrations and civilizations lead to this moment. You are the latest chapter in a narrative that began billions of years ago with the first living cells. Every ancestor who survived a drought, a predator, a disease, or simply the chaos of chance made your existence possible. You carry their DNA, their adaptations, their hard-won solutions to life's challenges. In a very real sense, they live on in you, and through you their legacy continues. And just as they passed the torch to you, you will pass it on, whether through children, through ideas, or through the influence you have on the world. Human evolution is not an abstract story happening to someone else. It is your story. Every breath you take is a continuation of a chain of life, stretching back to the very dawn of existence. And now the quiet wonders of human evolution begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the journey that made you who you are. From the first primates grasping branches in ancient forests, to the upright ancestors who walked across the African savanna. From stone tools shaped by patient hands, to the first cave paintings that spoke of dreams and wonder. From the spread of our species across every continent, to the rise of farming, writing, and civilization. You have explored how our ancestors learned to walk, to make tools, to control fire, and to share knowledge through language. You have learned that within every cell of your body lies the memory of an unbroken chain of life stretching back billions of years. You are connected to every ancestor who survived, adapted, and passed on the spark of existence to the next generation. You are connected to this story more deeply than you may realize. Right now, as you listen, your body is doing what it has always done. Your heart beats with the same rhythm that pulsed through your earliest ancestors. Your breath rises and falls as it has for millions of years. Your mind, shaped by countless generations, prepares itself for rest. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle pulse of life that has carried us from the distant past to this very moment, like the quiet hum of evolution that never truly stops. Tonight, as you rest, you continue the story. Your dreams, your memories, your hopes and fears are all part of the same grand narrative. You are not separate from evolution. You are its continuation. You are a small, warm presence within this vast journey through time, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that you belong to something ancient and beautiful, a lineage of survivors, thinkers, and dreamers who looked at the stars and wondered what might be. Thank you for joining me on this journey through the mysteries of human evolution. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of how we came to be. There are more wonders waiting, more secrets hidden in the depths of time and the quiet corners of our shared history. More gentle truths to drift through on quiet evenings. Rest well, and may the peaceful knowledge of your remarkable origins carry you gently through the night. This has been Drowsy Discovery. Good night.